we focus mainly on the Apache portfolio. We do a bit of other consulting, and when we started out about 10 years ago, we were mainly focusing on service mix, CXF, ActiveMQ, and moved into things like Apache Camel. And we work a lot as help on government contracts, medical contracts, facilities. We work with places like GE, and what we try and focus on is scaling, helping teams develop more resilient solutions, and getting around legacy applications. And this presentation will be about scaling. The key things about scaling is it's hard. How you do it will depend on what your problem actually is. There's no one patent solution to most use cases in the business world. I'm not going to give you a blueprint whatsoever. I'm going to give you a set of ideas. So I'll throw out a lot of frameworks. I'll show you how some things can be done. Think of it as hooks into what you could use in your existing applications today. How you want to maybe re-architecture. Because with every new framework that comes out there, say like Akka. Akka is a Scala-based framework that does actors, it does message processing, it does distribution. It could probably solve every single use case out there in the world asynchronously, but most of us have pretty large existing code bases. We have legacy processing, we have old systems, we need to integrate, we just need to tweak. We have deadlines, we have things that needs to be done. All of those ones you also need to address when you do this. And the picture is there because I thought it was funny, because that's actually how open source works. There are different sides of open source. You have some of the paid open source like JMO solutions. I'm the next one. I'm the next one.
He's the next one.
We have started.
Are you starting it?
And what I picked was an existing use case that we had. This is from a customer I'm working with right now. It's a learning company out of Boston. And they've been around for a long, long time. They build university solutions where you basically do quizzing. You have a student take a quiz. They get questions. Those questions have to be graded. They have to be correlated. And they have to be submitted back into what they call the grade book, which builds your grade, your study score, and is part of your whole semester and everything you're applying to. Now that application is really just a MongoDB. It's a Tomcat, it's JSPs, and there's a piece of BPEL-like business logic. I suspect most of you have similar applications. And what we are looking within this, one of the things I'm always after is how can we achieve this with the least amount of code, sorry. And what we will look at quickly is Apache Camel, Apache Giraffe, and here I'm just throwing out ideas. We have several committers to Apache Giraffe, so we use it in our offerings. I normally use it as a platform when I start building, because I like to write code in OCI. I like that modularity. We will introduce Apache ActiveMQ as a queuing library and queuing solution. That could be Kafka. It could be HornetMQ. It could be RabbitMQ. What we're after is something that has a queuing solution that can go across multiple machines. So we're talking in generic terms. We are looking at Apache Cassandra, because one of the things, it's the big thing. We have a whole track here on big data. But getting something like this in, if you can fit your data model in it, scale. Because you will eliminate, by eliminating some of the error checking and rigorous control of an RDBMS, you will be able to scale out more and do more asynchronous behaviors. And I'll keep on mentioning things like Akka. How many here have used Akka? How many have looked at Scala's actors? Okay, what I'm after is that Akka and Scala, with their actors, provide you with an asynchronous programming model. That's a model that's slightly more complicated to achieve in Java today. But if you think in JavaScript terms, think closures, think callbacks, what you're really saying is, instead of doing polling code, you want eventing. So instead of sending something to a destination, looping to say, are you ready, are you ready, are you ready? You send it to that destination and say, by the way, when you are done, you let me know. It's a much turned around programming pattern from, say, procedural programming, but it's very effective in building larger scalable systems. Then Apache CXF, we will look at to utilize for web services. And I don't know how many of you were in the previous 1-2 presentations ago that my colleague had on Apache Camel. It's another one of those. I always carry Apache around or Camel around in my toolbox with 183 components, EIPs, processors, exchange patterns, data transformations. You can basically solve any message-driven problem that you can find out. So Camel you can implement or you can utilize as a library in your existing applications. There's nothing saying you couldn't embed Camel in your existing servers if you have legacy code. You can pick and choose what's in Camel in its entirety because everything is modular. So you can take just a little tiny piece of it and we can integrate with about 180 to 200 things. So it's a nifty way of getting something up and running too. To use this and to say hook up to Hibernate, hook up to Cassandra, hook up to Mongo, you really don't need to run much about Cassandra, Mongo, or whatever thing you want to hook up to. If you look at something like the JMS component, it's about 2,000 lines of code that's been tested over the last 5 years in production, happily by people, and it has all the error checking, all the validation. You don't need to reinvent code. If you're using the JMS component and you say from JMS, you're invoking 2,000 lines of code. If you were to do it yourself, you need to write at least 80, 90 lines of code to open a connection, create a session, create a destination, create a source, and keep on parsing. And once you start parsing it, well, Camel handles that too, in that we will have what's called data transformers. So you can, if you have text messages, you don't need to write code like if instance of text message. No, just pull it out as a string. The Camel data transformers can handle that for you. And what we have in Camel, how many have read EIP patterns? Is it going to be only you the whole time? I highly recommend you build or you read this book, Hotkey EIP Patterns. It documents, how many is it, 63 patterns? I spoke to him a couple of years ago. There's a new book out in the works because what is missing from EIP patterns as published is state machines and conversational patterns. And that's what we're going to be talking about here, because that's kind of the key to how you cluster up an application. But what you have in Camel, by default, is the parts I've been talking about here. So you have messaging endpoints, about 180. And endpoints can be reading things, they can be producing. You can do things like stream from JMS, push into Logstash or Splunk. What it does is it helps you with the integration to all of these quirky things. You don't need to say, tell a developer, can you spend a week looking at how we should integrate JMS or how we should integrate it. It gives you the basics. Another thing I often do, because as a committer on these projects, there's no way in hell that you can look at all of them. So if I go out to a customer and I know I need to talk to InfiniSpan, I go look at the Camel InfiniSpan modules. At least I get the basics, or I have a unit test that show me how to do it. Then we have things like system management. You have control. Let's take an example. How many have written a JMS application? You can't answer it. So imagine you're listening from a queue. You're using auto acknowledgement. Okay? When your application is shutting down, how do you know when you're done processing? Are you going to use a timeout? Or are you going to say, after 5 messages processed, I'm going to be done? Or are you going to say, I'm actually going to say, I'm going to stop consuming in this. I'm going to drain everything I have left in my prefetch window. Or I'm just going to make a good guess and say, I'll let it go for 30 seconds and I'm going to kill -9. All of those things, they already exist in Camel. And as a library, Camel is one of those, it's handy to have, it's good to steal code from. Some of it, like any open source, isn't necessarily the greatest. But if you look at things like CXF components, JMS components, SQL, the string SQL, typical heavy usage component, we have a lot of people using those. And like I said, all of that in Camel, the cool thing about Camel is it's not a horrible you download. You're using Maven, I hope. What you do is you say, I want to use camel-jms. That gives you transitively all the dependencies you need. You cut down to what you need. In its smallest invocation, the default Camel context is just a bean. It's a bean, it's a registry, it's whatever components you need. So you're really only instantiating 3-4 Java classes. And this was more up a few years ago when we had the huge battles between should I use Mule, should I use Service Mix, should I use the other ESB. I think you've all seen that consulting picture of an ESB as the magic tunnel, and you just attach things. It's not that easy. And a lot of the use cases presented for ESBs are, I consume a file, I put it on JMS, and I store it in a database. Most companies do slightly more than that. And the flexibility of a library allows you to combine what I would call your code, the important part, the stuff you make money on, and you can forget about these integrations. The other one we were talking about is Apache Carafe. Apache Carafe is a container that came out of Service Mix originally. And what it really is, when Service Mix went from being JVI, Java Business Interface, to being OSGI-ified, to have a cold runtime, we broke out a console, logging, system administration on top of Felix. For this to scale, you don't need OSGI whatsoever. What I've found is that if you can get people to write code in OSGI, it will enforce decoupling. It will force you to learn a little bit more about the class path. And learning a little bit more about the class path is a good thing, because then you know why things are loaded from what and where. Due to import-export on a package level, and running in a container like this, we get version. So with this, we can run multiple versions of a service by just redeploying or deploying additional modules, implementing the same thing. And in the nature of OSGI, a core concept is services. That's another thing that allows you to scale within a container. How many deploy in Tomcat? How many use Hibernate or similar? If you deploy 50 WAR files, how many Hibernates do you end up with? You can't really share connection pooling. You can't share database. So you end up with multiple level 2 caches. If you use something like EH cache, you end up with multiple connection factories. You end up talking a lot more than you maybe wanted to DevOps, because you're blowing up that Oracle cluster. Because each and every one of your WAR file is using 10 connections. Because that's what your common DCP needs to do. By deploying this in a container like this, you can actually say all 50 of my WAR files, or let's call them in this case microservices, are going to be shared 1-2 connection pool to Oracle. And just by doing that, we've cut down on the resource use. Yes? Oh.
I've got a question. So OSGI essentially allows you to share the class path. Like right now, if you deploy the Tomcat, you can publish shared jars to a common class path. How is that solved?
You have multiple class loaders. So if you say sharing class path, you don't really. When you start something like Tomcat, you start from rt.jar, you go down to the endorsed class loader, which is endorsed shared blah blah. Then you have your app class loader. That's a tree. In OSGI, you have a matrix class loader where you control visible or invisible with version. So if you have 4 bundles, they can all load from each other. You do not have what you have, say, in WebLogic, where you have, I think it's called a firewalling class loader, where you can say this ear is allowed to see these things if loaded in this context. This is more of an open model, and nowadays, if you look at Glassfish, it's built on top of Felix. Carafe is built on top of Felix. And what you get, what's more interesting, is that you don't share class path, but you share instantiated objects. So imagine you have your Spring context, you instantiate a service layer containing your DAOs. Now every application, if they can import that interface, can use your service layer. And you don't need to dump all of that into every deployment, which means that your web service goes from containing Spring Core, Spring Beam, Spring Web Service, Commons, Commons Lang, Commons Util, Oracle JDBC. You're talking about 10, 15 meg. Your web service, if it's a JAX RS, is one class and a few dependencies. And those dependencies you can preload in the container. that makes it kind of lean and mean. And the last part, which I like, since you're exporting services as interfaces, you're forcing people to work with contracts. And when I do trainings, one of the things I harp on, to become good developers, you should be able to look at the JMS API. Just the interfaces. You can test against that. You can code against it. You can mock against it. If you can get people to understand that interfaces are cool, because you don't need a concrete implementation, you can much more rapidly develop. Then the other one we normally introduce is Apache ActiveMQ. This is to get queuing. It's the world's most used queuing system. There's currently a little bit of churn in the PNC there, because JBoss donated Hornet MQ. So Hornet MQ and ActiveMQ are merging right now. And I don't necessarily know what the outcome is, but given the flexibility of ActiveMQ, it's highly likely that somebody might just branch the existing stable ActiveMQ and make sure that that is there and maintainable. How many are using ActiveMQ? How many are using Hornet? That's why we want to maybe branch that, because ActiveMQ was built with not being EE, being easily embeddable, being connectable to almost everything, supporting REST, supporting Stomp. Stomp 1.0 and 2. A lot of the people who set that spec are developers on ActiveMQ. What the churn is about is that the JBoss side of the community is saying that the JBoss engine is more asynchronous and thus more resilient. Given the age of JMS, did JMS 2.0 really add that much fantastic popularity of Kafka? I can say personally, I've started investigating other solutions. Are there other things I could do? Java standards tend to get a little bit old sometimes. Cassandra, I started using Cassandra a few years ago. It's one of those big data solutions that I just love. Came from Facebook. The significant change between the Apache and the original Facebook implementation was that Facebook Cassandra was not multi-master. It was actually relying on Zookeeper, had a really complicated way of doing data modeling, was very specific to only a Facebook use case. So what the guys at DataStax that really were the founding incubator did is the first thing they did away with was Zookeeper. There's no single point of failure. Cassandra, write-wise, is insanely fast compared to other big data solutions. It has a pretty darn flexible distribution model. You can do cross-continent, cross-data center. You can scale it almost indefinitely. And how many have read Big Table or Dynamo? The papers? It's the same. I keep on answering. What they lead to is if you start using a NoSQL solution, let's ask that, how many have used NoSQL solutions? Do you have? Okay. I would recommend you to look at NoSQL solutions if you're looking at a lot of RDBMS in your current place. it is very invigorating when you can look at data modeling completely differently. You can skip a lot of the set constraints we have and go back to more flexible thinking. What else for concurrency? The best book I know on concurrency is Java Concurrency in Practice. I think it has in the foreword that there's only 2 people in the world that can write concurrent applications, and that's Brian Getz and Brian Getz. This is insanely hard to get right. This is one of the books that I quote the most when it comes to lectures, because these patterns are just, this is the way it has to be done. That said, how many have worked with NIO? Raw NIO and selectors. It's super duper hard. That's why you want to use something like Nina or Netty, where somebody who really knows it has done all the work for you. And you can once again focus on the business code. So, that's the introduction of the things we're looking at. Now let's go to our traditional stacked application. This is a real live application. I'm not going to name you the company, you can probably figure it out. It's based on Tomcat, MongoDB, and some additional Java jars running around. 100% synchronous. The response time between the browser and the server container is expensive because we're doing a lot of transporting of Java resources, JavaScript, back and forth. We have a bit of a glitch with the developers because the front-end developer has to know all of this. They have to know a little bit how to write a select. They have to know Angular. They have to know React. Ideally, they know JSP. They need to know some servlet code. And they're now being forced to start looking at things like queuing. And when you look at that developer profile, you really quickly get to something. They need to know so many things or have been in the company for such a long time that it's almost impossible to throw a new person in. And with what we are doing here, one of the tech leads on that project in particular, when he started, we had a lead time for a seasoned Java developer or JavaScript guy of about 3 months to be able to actually get into the code, commit, and work on it. So with the persistence, that's the first thing we addressed in this project and what we wanted to get rid of. We had massive problems in MongoDB. We had transitioned from MySQL and Oracle solutions. So we had probably used MongoDB the wrong way. We pretty much mapped the existing setup of RDBMS to Mongo, forced it to work, ran into a lot of right problems. So what we started looking at, to go NoSQL, you kind of need to inspect on how am I storing my data? Am I relying on joins? If you have applications that say 7 layers of left outer join, a NoSQL solution isn't good. You need to redesign how you store data. If you are super duper obsessed with transactionality, I can understand that if we're talking about credit card payment, but I'll let you know the sad truth is that even if you're transactional, the bank is still probably doing it as a batch job for the file, and they'll rerun until the funds get in there. But, and are you looking at using this as analytics? Then it's probably not for you. But you can combine it. So you can combine Cassandra and Hadoop, or you can combine Cassandra and Spark. Spark will do the indexing for you from existing data structures. But what you need to do, I think the worst use case for a NoSQL database or any database is OLAP solutions. If you need a data warehouse, you need a shitload of RAM or you need MapReduce if you want to solve it better. And if we say that we can do this data modeling, what you do is you start looking at your existing relational database. Okay? What most people do, and the first trick to do, is find what the natural keys are. How to correlate data. If you're building this where you have user ID 1, 2, 3, is there a better way of assigning, say, a key? Or do you just write down name and put in an ID? Write that down. Put in lookups, write that down. What I'm going for here is when you do big data like this, or NoSQL, always keep in mind how you want to retrieve it. And write not being expensive, nor read. There's nothing wrong with writing multiple times or writing the same data. And since you can more or less indefinitely scale this, if you do something like Amazon for Cassandra rings, go look at Netflix setups. They allow you to spin up a 1,000-node cluster that you can use for checkpointing, benchmarking, and seeing how this goes. And using Cassandra is pretty easy. What you need to do really is create a key space. You set up this is CQL3. Old school Cassandra used to be Hector and Thrift. That is now deprecated. The big difference between Hector and CQL is that Thrift allowed you to do dynamic column families, whereas CQL3 enforces a little bit more rigorous strictness, making it look slightly more like SQL. And there's a technical background to that. It's easier to replicate uniformly structured byte structures. And if you have the same amount of columns in a table, you always have the same amount of data that needs to be transported for replication. So that leads to speed improvements in Cassandra. It takes away a little bit of the flexibility. You can solve that in other ways. Then when you want to do this, the raw driver is the data stacks driver that looks very SQL-y and kind of works like JPC. We started using this a few years ago back in the Hector world, where we built a system for the country of Ecuador, and we looked at Hector and said, there's no way in hell we can ever get anyone text on this, because you have to say, I'm selecting from this table, this slice, these columns should be byte mapped to this is an integer, and I should have a long value here. So that guy there, Jeff, wrote a library that we call Hecate. That allows us to POJO map entities onto Cassandra structures. And that's another one of those, what we do here, underneath the hood, is that we're using asynchronous prepared statements. We're talking reuse. So in Cassandra world, with that data stacks driver, if you do that select over and over again as a raw select, the way Cassandra works, versus a prepared asynchronous statement, you're talking about 20 times speed improvement. Over large data sets, using that asynchronous capability can cut processing times on selects over a few million rows from 20, 30 seconds down to milliseconds. That's how much important the prepared asynchronous stuff on Cassandra is. And just to give you some ideas on why you might want to look at NoSQL solutions. We're not talking about huge stuff. This is from Ecuador. So we had 20 million users, 40 million transactions a day. We had 5 VM nodes running the Cassandra cluster. They really only need attached fast disk space. And we use Cassandra in this case as a cache. And the other cool thing is that you get, let's just now think that these web solutions are multiple servers. They're sitting behind a load balance. That's a typical setup. What we get here is that we have much more flexibility in how data is written, access to the data. We get cross data center distribution. If you use AWS again, you can set up east-west. You have that active-active. You get that for free. And to sum up the Cassandra part, modeling. You need good DevOps on the Cassandra side. It's fairly easy to set up, but you need monitoring. Then you need to inspect your code and make sure that you don't do these types of things. What we're doing here is a query where we're saying, I'm selecting from a table, I'm going to ignore the primary key, and I'm going to filter on something unindexed. And that's just the wrong data model. That's going to be super duper slow. It's going to suck. If you have taken this one and you have written down a Y column and you had given that a compound key where you said Y1, Y2, Y3, then you can do range queries and slices. And in that object that you write down that contains the Y, you contain the link back to X. So you do 2 lookups to do the same thing. Okay, let's get on to the next one. We've made the database asynchronous, and we have all of that going. Now we want to look at how can we get the JAX-RS or the web-facing stuff. How many do full stack web app plus web services in one container? Do you like it?
Not really.
So what we ended up doing here was we really said the front-end guys are really good at what they're doing, and they don't want to use Java. They want to use Angular, they want to use React, they want to use Node. So what we split this application into was we really took the whole front-end layer, the HTML5 did rendering. That part is now sitting in Node servers. They can spin up as many Node servers as they want. But what we do is we offer up everything as services. And for that, we're using Apache CXF. Apache CXF passes TCK, and apart from old school stuff like Turbo RMI and JMS that's in there, it's fully compliant with anything JAX-RS. And it's really a library there to help you make. How many have made a raw JAX-RS service just from the JDK? It's a lot of writing because you need to set up the namespaces, you need to set up the handlers. This stuff allows you to, with a resource class and 2 rows, start a server. And what we're looking at, in a normal JAX-RS application, JAX-RS 1.0, this is how you would annotate something. And that says that I will, in this method, I'll allow a get, and I will produce a string that's going to be the response, and that's what's going to go on the server side. Now this is 100% synchronous, you can have a little bit flexibility in here depending on what container you use. Newer Tomcat as well as Jetty have NIO connectors. Prior to this, Jetty started implementing and implemented first continuations. So a request coming in, the TCP thread, decoded, parked, and your resource class is then called. Once you supply the reply, Jetty will wiggle the two together to try and get down on thread usage. What still is going to happen is that your code part here, in the synchronous side, it is a blocking call. This is raw CXF. If you're using Camel to do this, Camel will actually do the continuations for you, but it's fiddly code because you have to keep track of who was the caller, who was the calling on the session, where is this reply going back to. Once again, effective but hard. So what came in JAX RS2.0 is support for asynchronous operations. And this is really cool. Think of this as a promise or a future. How many have used promises and futures? Good. So this allows us to continue processing. It allows us to wait for that response. And you can actually register completion and callback handlers. Not all RESTful Services Framework have support for this. CXF supports both of it. So you can actually monitor when somebody disconnects. You can see when a resource is completed. And you can write code that fully takes use of it. What it looks like is a bit more complicated than just the regular. You need to set up more wiring. So you need to set up a timeout handler. Here we're doing this in an executor service, and I'm doing that to simulate part of what's going on. So we're actually supplying the response in a runnable that's doing a callback to the web service. And one of the questions I get is, do you get better performance with this? Not necessarily. If you have a super duper fast web service that's serving up raw resources, you don't really have any complex computational things going on. A synchronous service will be faster until it chokes. It'll be faster until you completely run out of threads, and when you can't handle any processing. So what happens with an asynchronous is that you will get a behavior where you go up and you start maybe going slower, but you will be able to accommodate a whole lot more load. That make any sense? And here is just the same thing wrapped out so you can see what it's doing. And what I did with this, just to illustrate it, it's super hard to illustrate concurrency really well on a single machine. So if you have resources, test the living style. Use something like JMeter or Gatling. Use a lot of machines against many containers to make sure that you can achieve a load that will actually start benefiting from asynchronous behavior. And when I wrote this test case, we have that online in GitHub as well, just to illustrate and document. I took that executor, and I had a lot of debate with colleagues about this. So what I did is I put a thread sleep inside of that executor to simulate a bad DAO. You could put a for loop, you could do something. What you want to illustrate is that this is going to go. So on my Mac, 500 users, a random delay of 200 to 500 milliseconds, we're hitting about 7,500 requests per second with the asynchronous setting. The other completely non-technical observation, if you have Macs, you know when the fan starts spinning, here it was pretty decent. And response times were pretty uniform. They kind of bunch up. If you had a super fast synchronous service, the synchronous is going to sit here. They have really, really low latency because they have much less processing. So we're introducing a little bit of overhead to get the scalability. Now this is with the sync. And here is introducing a bit of a block in the synchronous service. So with this guy, what happened is I quickly went up, I more or less choked right away, and the fans started going like crazy. Because I'm choking on CPU. I can't get any higher. And this kind of illustrates what I'm saying. We also ended up that it took almost double the amount of time to process this. Because without the asynchronous behavior, I can't handle a background or a work queue. And the synchronous response times were much more all over the place and much higher in general. And this, what happens next when you start stretching this? That's when people say, oh, the load test failed, because we just fell over. What's going to happen is that Gatling is just going to say, I can't even correlate this. I get timeout, timeout, timeout. Boom, I blow up. You wait a few seconds, oh, I just start losing it. With these techniques, just with the database and the asynchronous behavior, the current production system we have right now was based on Tomcat Mongo, like I said. They are running over 3 nodes, 16 gig JVMs, about 163 requests per second. This sounds super little, but think of 1 request as a complete quiz in university. So we maintain a boatload of state. With the same techniques, we are running on virtual hardware, a AWS medium or large instance with 3 gig of RAM, the same load. And we're handling the same. Yes, there were better people developing the second solution, but we are, in principle, doing the exact same amount of load. So that's how much these techniques can actually give you. And we'll run through the last part. What we needed in this system is this business logic. What that business logic really does is that we allow for the editing of content, but editing that content is a super expensive operation, and it's done asynchronously. So the use case we have here is that when somebody calls here, this application, the web application, is going to call another web application multiple times to say, fix this, fix this, fix this. Then it's going to shove it into the database, return and say it's available. This is a really blocking, super expensive call. So we wanted to get that asynchronous as well. On that business logic side, we apply the same. The asynchronous, and what do we need to fix this? What we really need is something that we can share data between nodes. You might think we could use Cassandra. No, because Cassandra, because of how it deletes, isn't good for rapid insert, delete, insert, delete. Those deletes don't happen until 10 days later by default. So you're going to fill up a Cassandra ring if you start using it for those things. So what we will use here is Hazelcast. You could use Infinispan. I just like Hazelcast because it's one jar, super easy to get started with. And what we're using in Hazelcast is one of the features. So for free now, I have an entry listener. That entry listener allows me to perform actions on data when they've been added to the memory grid. That gives me an eventing system. And all you need to pipe up Hazelcast in your existing application is 4 or 5 lines of code in XML file. And Hazelcast works unicast, multicast. It's EC2 aware. You can combine these so you can actually run if you have a VPC or something like that. Hazelcast in the cloud, talking to Hazelcast in your local data center. And what it really is, how many have used Hazelcast? It's a map. From a programmer's perspective, it's a map. And then you have a few utilities around it. And that's what makes it so cool. Because you get a map-based TW store. You can shove data in it. And then what we're using here is one Hazelcast interface. And that entry listener allows us to not have to loop. It gives us similar behaviors to all the suppliers and consumers and providers. You have some of this now in JDK 8, but this is just a nifty way of saying somebody added something to this map. I'm going to use it. And what we're going to do to get this working is that synchronous operation, we eliminate. We're actually going to return a void. And the calling party, when they say process this for you, now passes in a correlation ID. Once the expensive part is done, they put that out on a queue. And what we do is we implement that entry listener and say we have two maps. We have one map of the stuff we sent out, correlation IDs. We have a map that's memory distributed that gives us back events when something has been processed. That gives us the capability now to correlate this. And since we can correlate this, we end up in a really cool state because now we have an asynchronous web service to asynchronous with a queuing behavior, with an asynchronous database, and a memory grid. So that whole system now has gone from one monolithic WAR file to what I didn't really illustrate here. We have a forest of node applications here that we are servicing across these load balancer, asynchronous behavior. We can scale out the business logic boxes because they're no longer utexes. They're no longer DeepL solutions. As a matter of fact, I don't give a hoot who processes. So the first one that can pick it up is going to do it. Would it have been better to put that request reply completely over JMS? Probably. But we didn't have time, and we had existing services that we knew were working. So just putting the reply back out on the queue kind of gave us enough for this time being. Questions? Yes?
That book that you referred to at the beginning of the talk about patterns?
Sorry?
The book that you referred to at the beginning of the talk relating to patterns?
EIP patterns.
EIT?
EIP, sorry.
EIP.
There is one more book which is the pattern based consumer pattern.
Yes. There's EIT ERP or ERP patterns. This is 63 or 68. I think it's 63 different patterns are described. And they are things like queue consumer, polling consumer. I wouldn't treat it as religion. I would treat it as it's a damned handy vocabulary. Because if you learn this correctly and you know the UML symbols for that, you can describe a whole lot of these use cases very succinctly and distinctly. And somebody who has read the book is going to say, oh, I know what you mean. Okay, we're good. Cuts down on development time, cuts down on documentation.
There is no other follow-up. Is that missing two patterns?
There's a few patterns missing. It's state machines and conversational patterns. What we just did here is what we're doing with this one is a conversational pattern. I'm saying to the web service that I'm going to call you and I'm going to give you an identity to correlate on. Okay? Then the other system says, here's your reply with this correlation ID. And that gives me across platforms, across systems, conversations going on with request reply instead of me going, sending, waiting, or even worse, sending, setting up a lister and polling. Are you done? Are you done? Are you done? Are you done? That's kind of like that bash for loop that people used to write on old banking system. That when you do heavy files, you choke the CPU. You're done, right?
No.
Yes.
Are there any plans to support like Apollo in Corrupt instead of 5.8?
Apollo is actually dead.
Oh, really?
Yes. Apollo hasn't been maintained in 6 months. And the guy who wrote most of it, unfortunately, works for JBoss. So I think he's a little bit forced to be on the Hornet side. Which was a pity, because that was a great starting point.
Yeah. Okay.